I'm Junchen from CMU. This work is done with Shijie Sun at Tsinghua University, Vyas Sekar at CMU, and Zhang at CMU and Conviva. In this talk, I will introduce Pytheas, a system that enables data-driven quality optimization for internet applications. Now, drawing on a parallel from ML literature, I will formulate data-driven quality optimization as a process of real-time exploration and exploitation, and show how to implement it in practice. Now, let me first spend 1 minute to walk you through the key points of the talk. Many recent projects have shown that the quality of many applications like video streaming could be significantly improved through a data-driven approach, where the adaptation of individual sessions is driven by the quality measurement of many other sessions. Okay. However, prior implementations have always formulated this process as a prediction problem, which we argue is incomplete and suffer from many limitations. Now, instead, we draw a parallel from ML literature and argue that the data-driven quality optimization should be cast as a process of real-time exploration and exploitation. Now, the key challenge, however, is how to run exploration-exploitation with fresh data from geo-distributed sessions at scale. Now, to address this challenge, we developed a system called Pytheas, which uses group-based control mechanism. The key idea is that application sessions sharing the same features like IP prefix or location can be grouped so that we can run exploration-exploitation at a per-group granularity. And these per-group processes can then be independently run in geo-distributed clusters. And as a result, we use video streaming as a use case and show that Pytheas can improve video quality over a prediction-based baseline by 30 to 78%. Now, first of all, ensuring high quality of experience, or QoE, is very crucial for applications such as video streaming and VoIP. But their quality today is not ideal. For instance, we see a lot of video sessions suffering from bad QoE, such as buffering interruptions or low-resolution videos. And I believe you all have experience of watching online video with a lot of stalls, right? Now, one key reason for today's suboptimal quality is that adaptation of individual sessions is driven only by its own local information. For instance, video players often use a local trial and error logic to select which bitrate to use and which CDN to stream the video from. Now, some recent projects have shown that a new data-driven approach can achieve promising QoE improvement. Now, today, many service providers, many application providers can maintain a real-time global view of QoE measurement from many clients. Now, this opens up a new opportunity for a new data-driven approach where the adaptation of individual sessions can be informed by this real-time global view. Okay. Now, for instance, prior research has shown that using data-driven quality prediction, one can reduce the buffering time of video by 30%. And similar improvement could be achieved in the context of other applications as well, like web and VoIP. Now, in prior work, a data-driven approach has always been formulated as a prediction-based workflow. For instance, when a new video session starts, it needs to select the CDN and bitrate. Okay? Now, the basic idea of a prediction-based workflow is to first collect measurement data from many different sessions, and then build a QoE predictor based on this measurement data. Now, such predictor can predict the QoE for any future session if it were to use certain bitrate or CDN. Now, based on this QoE prediction, we can then decide the best CDN and bitrate for individual sessions. And such prediction-based workflow often happens on time scales of tens of seconds to minutes. While this prediction-based workflow shows promising improvement, it has two fundamental limitations. First, the data collection process actually depends on its own prior decisions, and this could lead to prediction bias. For instance, so basically, we will always have more measurement data on decisions that are historically better and will not have enough data to reliably estimate the quality of other sessions, of other decisions. Okay? For instance, imagine you're selecting between two CDNs. Okay? And for now, if CDN 1 is better than CDN 2, we're going to assign more sessions to use CDN1 and lost visibility to CDN2. So if later on, if CDN2 becomes better, you won't be able to detect that, right? Now, second, because it takes time to aggregate sufficient data to retrain the prediction model, these systems often update qualitative predictions periodically on coarse granularity, on coarse time scales. And this might result in suboptimal quality due to its slow reaction to qualitative variance. Now, in this talk, I will first introduce an ideal abstraction for data-driven quality optimization. Then I will show how to realize this abstraction in the networking context. Okay? And in particular, this talk will use video streaming as a use case. First, to address the limitations of prediction-based workflow, we draw a parallel from ML literature and argue that the data-driven QE optimization should not be a prediction process. Instead, it should be cast as a process of real-time exploration and exploitation, or simply we call it E2 here. Now, at a high level, E2 formulates the measurement collection and decision-making as a joint process. Okay? Now, the intuition is to continuously strike a dynamic balance between exploring suboptimal decisions and exploiting the currently optimal decision, okay? Thus fundamentally addressing the shortcomings of prediction-based approaches. Now, here's a quick review of what E2 is. Imagine you're a gambler, okay, and you can pull one of multiple slot machines. And each slot machine has some hidden reward distribution. Now, each time you pull a machine, you will get a sample of its reward. So your goal is to maximize the main reward after a limited amount of pulls. So naturally, you want to do some exploration and then exploit the best slot machine, right? Now, of course, the reward distribution can change over time. So this is a continuous process. Now, this is very similar to our problem, right? We have sessions, we have decisions. And when a session uses one decision, it gets a sample of its QoE. Okay? And the goal is to optimize the overall QoE over a set of sessions. Now, as I said, the benefit of casting our problem into E2 is that the E2 techniques naturally solve the limitations of prediction-based systems. But it's actually very challenging to design a system, an actual practical system, to apply the real-time E2 abstraction in networking context. In particular, there are two challenges. First, these sessions are actually in different ISPs and with different network types and using different devices. So there's no globally best decision. So the first challenge is how to capture the similarities and differences between these sessions. Now, a baseline solution might be to make different decisions based on their geolocations, right? But as prior work shows, video quality depends on many complex factors, such as platforms, content, and network types. So we need a model to systematically capture these factors that may determine optimal decision. Second challenge is that how to respond to geo-distributed sessions in real time with fresh data. Okay? Now, baseline solution is to leverage the geo-distributed infrastructures widely deployed by today's application providers. The idea is that we can use a centralized backend cluster to train models, okay, and then push them to geo-distributed front-end clusters that are very close to clients. Now, so when a client requests decisions, the nearby front-end cluster can respond with latest model catch locally. Okay? Now, the problem here is that the communication between front-end cluster and the back-end cluster is not in real time. Instead, each front-end cluster will pre-process the measurement data and then sync up with the back-end cluster every few minutes in order to reduce the bandwidth usage between clusters. So this poses a fundamental trade-off between data freshness and global view. If we run a global E2 in the backend, it won't have fresh data, right? And if we run it in the front-end cluster, we won't have enough global data to train the complex relations between sessions. To address these challenges, we developed a system called Pytheas, which uses the group-based control mechanism to run real-time E2 in networking context. The key intuition is that application sessions sharing the same features like IP prefix, location, or platform can be grouped so that we can run real-time E2 logic at a per-group granularity. And these per-group processes can then be independently run in geo-distributed front-end clusters. So such group-based control mechanism is enabled by 3 ideas. The first idea is that sessions can be grouped based on critical features, so that clients in the same group will share the same best decision. Now, the notion of critical features is borrowed from our prior work. The idea is that if you imagine video QoE as a function of feature values, the critical features are a subset of features whose values ultimately determine video QoE. Okay? So, for example, if a video session is bottlenecked by its local ISP, then its critical features will naturally include location and ISP. Okay? Now, in general, the notion of critical features has been implicitly used in many related projects as well. Now, because the sessions in the same group share the same best decision, we can now decompose the global E2 process into per-group E2 processes. Right? Here, sessions in the same group will share the same E2 process, which is a kind of a variant of the standard upper confidence bound algorithm, or UCB algorithm, so-called. Now, grouping sessions based on critical features helps capture the complex relations between sessions. But it doesn't solve the second challenge. That is, how do we make real-time decisions based on fresh data? Okay? The idea to solve this problem is that critical features are often aligned with narrow locality. Okay? That is, sessions who match on critical features often share certain narrow localities, such as IP prefix or location, so that they will be likely to be received by the same front-end cluster. Therefore, each per-group E2 logic can run independently in a front-end cluster with fresh data of sessions in the same group. Okay? Now, the final missing piece in this picture is how to group sessions. Right? Now, as I said, the sessions are grouped based on their critical features. Now, training critical features requires a global view, but it doesn't require fresh data, right? Because the critical features, as prior work shows, are very persistent, typically lasting for tens of minutes to hours. Therefore, it's very suitable to run the session grouping logic in the backend cluster with the global view. Okay? So at a high level, Pytheas physically separates the offline session grouping logic from the real-time per-group E2 logic. Okay? Now, this allows Pytheas to group sessions based on a global view while making real-time decisions based on fresh data of other video sessions in the same group. Okay? Now, Pytheas is open source and can be easily deployed in public cloud service like Amazon AWS or CloudLab. Now here, the front-end clusters will interact with video clients by standard HTTP protocols. And each per-group E2 logic will run inside a front-end cluster. And the client grouping logic will run in the back-end cluster and periodically updates the client groups with front-end clusters. And notice that these implementations are all based on open source software, so Pytheas can be used by everyone. Now, for the interest of time, there's a bunch of other topics I didn't cover in this talk. For instance, a natural question is that if the sessions of the same group are mapped to different front-end clusters, so how do we run E2 logic across multiple geo-distributed clusters? Right? Now, you're welcome to check out these details in our paper. Finally, evaluation. First, we evaluate the improvement of Pytheas over a prediction-based baseline called CFA, which was published in NSDI last year. We use a real-world data set of 8 million video sessions and use trace-driven simulation to evaluate Pytheas on 2 standard video QoE metrics. Okay? On the left-hand side is join time. Join time is the delay before a video starts playing. Okay? So lower the better. Right-hand side is buffering ratio. Buffering ratio is the percentage of video session duration spent on buffering. Again, lower the better. Okay? Now, x-axis on both figures is the improvement of Pytheas over CFA. So if the value is positive, that means Pytheas is better than the prediction-based baseline CFA. Otherwise, CFA is better than Pytheas. Okay? Now, the y-axis is the CDF over all sessions in the data set. Now, you can see that Pytheas doesn't improve over CFA over every single session. because E2 always requires some sessions to explore suboptimal decisions, right? But overall QoE still gets better. The mean QoE, for example, can be improved by 6 to 30%, and 90th percentile can be improved by 24 to 78%. Now, let me also put these improvement numbers into context. It's widely known that reducing buffering time by 1% can increase, on average, watch time by about 5 to 8 minutes. So such improvement is a big deal for content providers. Right? And next, to evaluate the scalability of Pytheas, we run our end-to-end implementation across multiple instances in CloudLab. These instances are grouped to form 2 front-end clusters and 1 back-end cluster. Each cluster includes 5 to 35 instances. Okay. Now, left-hand side shows the throughput of, so how many sessions can be handled by a front-end cluster as a function of the number of instances in it. And right-hand side shows the throughput of back-end cluster as a function of the number of instances. And we see that the Pytheas implementation is almost horizontally scalable. Okay? And also, to put these numbers into context, with only 30 CloudLab instances, Pytheas can handle the workload of YouTube, which is 5 billion video sessions every day, with feedback delay of less than a second. Now, to conclude the talk, many recent projects have shown promising quality improvement by a data-driven approach, where the adaptation of individual sessions is driven by the quality measurement of many other history and concurrent sessions. However, prior systems have always formulated this data-driven approach as a prediction process, which we argue is incomplete and has fundamental limitations. So instead, we draw a parallel from ML literature and argue that the data-driven quality optimization should be cast as a process of real-time exploration and exploitation, or real-time E2. Now, the key challenge, however, is how to run E2 with fresh data from geo-distributed clients at scale. Okay. To address this challenge, we developed a system called Pytheas, where the key idea is that application sessions sharing the same features can be grouped so that we can run E2 at a per-group granularity. And these per-group processes can then be independently run in geo-distributed clusters. Now, using video streaming as a use case, we showed that Pytheas can improve video quality over a prediction-based baseline by 30 to 78%. Now, if you forget everything I said in this talk, here are 2 takeaway messages I want you to remember. First, data-driven quality optimization should be cast as a process of real-time exploration and exploitation, or real-time E2. And second, the key technique to realize real-time E2 in networking context is group-based E2. Okay. With that, I'm happy to take any questions. Thanks.
Shankar from AT&T Labs. So really good work. I'm very impressed with the kind of frameworks that you have built. I'm curious how you come up with this set of features, because feature selection is obviously the most critical aspect of it, which determines how much you are able to exploit these option of grouping things together, right? So do you have any ideas on how you could pick those features? What are the relevant features? And is there any thoughts on that?
Oh, good question. So you're really touching the key part of this series of work, which is, first of all, what are the features you need to collect from from these application sessions, right? And second of all, what are the important features among these, right? So what's typically the important features? So unfortunately, these 2 parts are not a key part of this work. This is mainly addressed in our last paper in NSDI last year. But I can tell you the features we use in this work are basically features about geolocation and IP prefix, and also content and platforms and server-side features like which CDN it is using. So these are kind of, I would say, the basic idea to collect a comprehensive set of features is to cover network problems and client-side problems, server-side problems, and also application-level platform problems. And to a second part of the question, so what are the critical features and kind of important features? That's a very difficult question to answer because it really depends on different clients. Some clients, the critical features are the last mile, right? So their last connection, wireless or cable. For some other clients, it's actually depending on which kind of content he or she is watching. Like if it's a live video content, the quality issue may be very different from if it's a VOD content. So I can talk to you offline about different cases. There are many heterogeneous cases I can talk to you about, but this is the key idea.
Okay.
Thank you.
Okay, so I have one quick question. I mean, given that you have done a large body of work in the same area, so I mean, do you think if you ended up with this solution before the other set of paper, you wouldn't have done those, or they're still required in different scenarios and useful?
That's a very good question. I guess you're asking how close to optimal we are, right? So I have two parts in the answer to that. So I think first, there's no good definition of optimal, right? So the nav performance or video quality is very dynamic and has a lot of randomness. So I would say if you use the existing measurement data set to quantify the optimal, that would be overfitting. So it's just saying, first of all, it's very hard to define optimality. And second of all, the video quality, so the video ecosystem actually evolving constantly. So there are many, kind of a new applications on video streaming that's it's a very increasingly demanding. Right? For example, 4K video has much larger demands on the nav performance than traditional YouTube-style VOD video. Right? And also, if you think about Facebook Live, it's kind of a live video streaming with very stringent requirements on latency. So I would say the bar is increasing as well.
Okay.
Thank you.
Okay, let's thank the speaker one more time.